Okay, tell you what, I'll
I think I started. Yeah.
okay, great. I think this is working fine. Yeah, Frank, go ahead and introduce her and then we can start the call.
Yeah, no problem. Maybe you'll find out.
Can I close this?
It will wait a few seconds.
Okay,
so,
sure.
just go into full screen.
Okay, so I just got all this information from your LinkedIn homepage. Right, so yeah, it's my pleasure today to introduce you today's speaker, Zijia Yang. Zijia is a third-year computer science undergrad at the University of Cambridge, where she has earned first-class honors and chairs Girls Group ML at Computer Lab. So she previously studied at Peking University, and her work right now bridges AI research and industry. She has conducted research at Cambridge AI Safety Hub, and she interned as a software engineer at Meta, and will be joining Tudor Investment Corporation as a quantitative developer. And so Zijia joined us as an undergrad research assistant, and she works with me on like MAE for TESSERA to basically just incorporate spatial information into TESSERA's embeddings, and she has done a pretty good job. So yeah, today, so the floor is yours, Zijia.
Yeah, thanks for the introduction, Frank. It's very detailed. And hi, everyone. I'm Zijia. I'm an undergraduate student at the department, and I'm doing my third-year project under the supervision of Frank. And today I'm going to present my work enhancing Geospatial Foundation Model representations with Masked Autoencoders. So, yeah, you can see the slide. So, like everyone's familiar with our old new friend, TESSERA. So it is a geospatial foundation model which has 128 dimensional, 10-meter resolution analysis-ready embeddings that is currently state-of-the-art at several benchmarks. And it stands for temporal embeddings of surface spectral for Earth rotations analysis. Here I highlight temporal embeddings because it's kind of relevant with what I'm doing later, because it's used the time series of observation data of like a pixel on the Earth to train the models, and that has some kind of implications with the motivation to use MAE later. Here I copy paste a processing pipeline from the TESSERA paper. As you can see, like the time series information from different modalities are extracted into this like D pixels, which has all this like temporal signals of a single pixels, which is a 10 meters times 10 meters square, like grid on Earth, within this specific modalities information, and they are being sampled and processed by this encoder and project onto our latent space, where we use Barlow twin loss to do this reduction called a reduction removal kind of self-pretraining scheme. So I would like to introduce some maybe research gap that I identified with this pretraining process. And although TESSERA embedding is a very powerful thing, like embedding to use for downstream tasks, it still has some like limitations or potential room for improvement for downstream tasks and maybe more scalable deployment. One thing I think concerns with the 128 dimensional pixel-wise embeddings. They are very costly to store and process at scale compared to other geospatial models like AlphaEarth, which only has 64 dimensional. So, and also another one is with the temporal kind of processing. It has this spatially agnostic training in inductive bias in it, because it only concerns like each individual pixel as an individual data points in the training pipeline. So also it adds a global shuffling to sample these pixels from like different locations around the globe. So it really removed the spatial awareness of a single pixel, and it's a pixel-wise model. So it cannot generate like a patch-based embedding for a single patch, but there are a lot of correlations or like redundancies in like a neighborhood information. So I'm wondering if I could use this spatial information to remove some redundancy to further either like compress it into a more condensed, but also like semantically rich embedding, or by incorporating this neighborhood information, I can further enhance it, but instilling more like spatial awareness into it to make it more powerful and more useful for downstream tasks like semantic segmentation. Yeah, so that's the whole motivation for this research. And please interrupt me if you have any questions or things that should be more clarified. And the method I'm using is called masked image modeling. So originally I was just going to use Masked Autoencoder with such a variance, variance in masked image modeling. But later on I discovered, I could try with more encoder architecture. So I incorporate more like this MIM kind of pretraining framework into it. So here's a general idea of how to do like a masked image modeling. So you have the input, and it's first like patchified, and then apply a mask onto it to mask some regions of the input to create like a bottleneck for the masked autoencoder to reconstruct it back, and use the encoder to project it to a latent space and a decoder back. Here I use a asymmetric design because I really want to have a powerful, like a strong latent space rather than having a powerful decoders. So I try to keep it like lightweight compared to the encoder. And we have the output. And here I apply the mask to illustrate that the loss is only computed on the unmask, on the mask region instead of the whole images. And this is just an idea. So here I experiment with two encoder backbone variants. One is the vanilla Swin Transformer, and this one is Swin Transformer. And here I want to like highlight that there is like a difference in their representation. For a Swin Transformer, for the encoder, it first like patchify the image and then flatten it into a sequence, because transformer is a sequence to sequence model. So it cannot process image like originally, but we can flatten it in a sequence. And then I project the embeddings to like a larger like models embedding space, and keep that dimensions down, like process it through several transformer blocks onto a latent space, and then use a decoder to do it back. But decoder is not part of the encoders, it's just to show that it will try to reconstruct the original input. And here the swing is a variant that is good for semantic segmentation task. And I think it borrows some ideas from like the UNet architecture that I will talk about later. So use first is use a local window instead of attending to all the pixels on the whole image. It's only use a local window that confines attention within that window. And to enable communication between different windows, it has the shift-based configurations that add more connections between windows. Also here it shows it has a hierarchical representation, and it maintains to the spatial structures within each blocks. So instead of flatten it, it has like a patch merging layers that at each stage, it will reduce the spatial resolution by a factor of 2 each side. So the spatial side will be down by 4 in total, and it will double the channel dimensions. So the entire dimensionality reduced by 2 with increasing channel dimensions, but reducing spatial size. And there are several stages, and eventually it will get a latent space that's the same size with the Swin Transformer. So it do it like gradually, incrementally, instead of just at one step at the patchify stage. Yeah, so that's this difference. And here is like a detailed pipeline of the encoders I use. And for this one, it's the vision encoders, which the patch size of 8, mask ratio of 60%, and I use smaller dimensions that is consistent. It's like is 768. So first, the patchify will split into patches and also flatten it into a 256, which is square of 16. So 16 is 128 divided by 8. So that's how it is patchify and also flatten it out. and add positional embeddings, do the patch shuffling, which is just like shuffling the patch and randomly drop the last 60%. So it's like kind of conserved as the masking strategy in Vision Transformer because it doesn't preserve the 2D resolution. So the scheme here, which is like a binary mask, doesn't apply to Vision Transformer. So it does this patch shuffling and randomly drop for masking. And then this dimension of like input will go through the transformer blocks to produce latent space. And here the dotted lines denote during model inference, we skip the masking phase. So we input the whole image. So it will keep these dimensions down to like 16 square times the model dimensions for latent space. And it's like a sequence. And for Swin encoders, we have like a patch size of 2 because here we can decouple patch size with mask size. So they're like different. We can have patch that's like smaller, but we apply mask that is like larger. Mask size is similar, it's the same with the patch size in Vision
So what do you mean the mask size compared to mask ratio?
Mask size and mask. So mask size is the size of like a square, like a mask.
I see. Oh, it's a mask of 8 pixel mask.
Yeah, 8 pixel.
It's like a checkboard.
Yes, the checkboard.
Okay.
Yes, and mask ratio is what percentage of patches are.
And the upper one also mask size is 8 or?
Yeah, its mask size is 8.
Okay.
Because like the patch size is essentially the mask size because you are doing this patch shuffling then drop.
Okay.
So you drop like a patch size, like a patch, which is a mask size of 8 in this phase. But in Swin, I will show you later, like it does this like binary mask. So it has a match size of 8 and it will apply to like a grade of patch, which is we can use like a smaller, this is 2 here.
Mm-hmm.
And here you can see it has this hierarchical representation where it gradually downsamples and upsamples gradually downsample the spatial resolution while upsampling the dimensions. It reach it's also 18 square times the model dimensions. So I try to keep the latent representation size like consistent within the 2 encoders to kind of better compare them. And because of the difference in their like nature for VIT.
I'm sorry, just in the previous slide, where does that 76 come from? 76 by 768 after the patch shuffle, where is that 76?
This one, 64.
No, 76 by 768 after the patch shuffle.
Oh, that one. It's because it's times because it's 256 times 0.3. Because
0.3. Oh, okay.
Because the 0.4 because the mask ratio is 0.6 and then it's get rid of the
it's left over. Okay.
Yeah, so it's like a sequence.
Right.
But during the inference phase, you don't do this.
Right, you get the whole thing.
Yeah.
Okay.
And because of the natures of different like backbone for VIT, it use masking as like shuffling and dropping. But for Swin, you need to keep this 2D spatial structures. I use different framework, and the framework is like naturally kind of invented to accommodate this to architecture, I think. So for Swin, it's called MAE, it's Masked Autoencoders. It has this pipeline of what I just introduced, positional embeddings, masking, and dropping. So there's a bunch of sequences. I only have the remaining visible patches here to be used.
So do you have positional encoding as well? For the positional embedding, do you have a XY position as well?
Yeah.
Okay.
I think so for the Swin, the reason why there's no positional embedding because the embedding is encoded in the attention. Right. In the attention modules.
Oh, because you're pushing the whole thing, including the masking. Yeah. And what about the day of year? Are you putting that through as well?
What is the
if you have times, this is all.
No, this is not time. This is not time. There's no like.
That's not good.
This is like
a
embedding.
Yeah, this is TESSERA embedding. So it has It's
Right,
like an
right,
aggregation of.
No, I understand that. Okay.
And
Yeah, no, but it is possible to time shift TESSERA annual embedding start time, and then you have DOI, but you don't need that here. Okay, that's fine. Okay.
here I like simplify it, but for the pretraining, like the input, I sampled from multiple years.
You did.
So
Okay.
yeah, it's a mix of different years to our embeddings.
Okay.
Yeah, but here I just show if I
But
have.
that's not necessarily good. I mean, sorry, the whole patch comes from 1 year ago.
Yeah, the whole patch come from 1 year,
Okay,
but they have like more, like the patches are from different years.
Okay,
It's like a
that's
mix
okay.
of different years, but
Sure.
the one patch is just 1 year.
Okay.
And this is the VIT backbone, and I add mask. I need, because I use a convolutional decoder, which I will choose later. So I need to ask back the mask tokens to reconstruct it. And for the Swin backbone, it has this binary mask, which is similar to what I first introduced here. So I use this like masking scheme to keep the 2D spatial structures. And also because it's originally like consistently like 2D, so I don't need to add positional embeddings in the pre-processing steps. And it has this hierarchical representations where each way is like a receptive field at each stage. So this is the decoder I'm using. It's a very simple convolutional decoders, which it has only 1 million parameters compared to like 30 million in the encoder. So it's a very strong kind of asymmetric design. And for VIT, I need to append mask tokens and I shuttle it back and reshape it to like a 2D structure to be able to process by the convolutional decoders. Yeah, and eventually it will reconstruct the original dimension back and to compute the loss between the original one and the reconstructed output. So I conduct a comprehensive ablation study on different parameter values of the encoders. Here are all the things that I tried. First is most importantly the compression ratio, which concerns with the latent resolution, and also the mask ratios. The data scaling refers to what is the size of like data set I tried in the pretraining phase. And the last two are Swin only. The first is patch size and mask size, which I think I explained. And why they're Swin only, because for Swin Transformer, the patch size is equal to mask size. And they are also related to the latent resolution. So the latent resolution is the original 128 divided by the patch size, because you did this downsample once in the patch embedding layer. Is that like clear for everyone? Yeah.
Okay, I think I missed one detail, but
Yeah.
patch, when you say patch, this patch embedding layer is the patchify layer?
Yeah, yes, the patch embed layer is the patchify layer.
Okay, because you called it patchify earlier. Okay.
Yeah, it's the patchify layer. So the patch size is 8 and latent embedding, latent resolution is 16. So that's like fixed. But for Swin, you can first patchify it and then apply a mask. If you patchify it, then it becomes 64, but you will gradually downsample it to 16. So it can like decouple the parameter values to have like multiple things that I can adjust and try out if they kind of affect the like the eventual outcome. So here is the table of all the configuration that I tried, and there are the parameters, and I'll just to show it for you to know that how I've tried several.
And how did you pick this table? How did you make that table?
What do you mean?
How did you decide on these parameters?
Oh, how do I decide on parameters? I guess for the latent resolution, it's like the most critical kind of parameters. And I tried different things. I tried with like 8, 4, and 16. And I think 16 constructs the best. Like I will show it later. So I kind of fixed on this default settings and try to adjust around it. So every kind of combination is compared with the default setting. So default is set like a baseline. For what I think.
Okay, so you're choosing the default and then doing variation of one parameter along each dimension from that baseline. Okay.
Yeah, that's one.
So when you do this kind of thing, essentially trying to do is doing a partial derivative along each of those parameters.
Yeah.
Choosing the default carefully is very, very important, because if you choose the wrong default, you end up with exploring part of the space which is not the right path necessarily. So
Mm.
in your report, when you do write your report, make sure you explain why you chose this to be the default.
Mhm.
It's and yeah, what you did to, you know, it's not just a random choice, it has to be very carefully chosen.
Okay, sure. I think, yeah, I feel like it's a bit hard to like justify why the default is like the golden standard, but I'll like, yeah, I'll see if I can further explain it better.
Okay.
Yeah. And here I present the like retraining reconstruction. So the first two columns are the baseline, and this column is the raw embeddings. I use the first three channels as the RGB values in order to visualize it.
You should also explain what is NNI.
Oh, yeah, the NNI compression. So because this is like reconstruction, and I want to show like a simple compression and reconstruction scheme without any like learned component to be like a weak baseline to show that this framework really learns something instead of just like compress and reconstruct. So the NNI use nearest neighbor interpolation. So for it use it for like downsampling and upsampling. For downsampling, pick the one pixel within like n times n grade, and for upsampling it will choose the like nearest pixels within that, so everyone kind of gets the essence of it. And there's no like learned components, it's not a neural network, it's just a very simple like downsample upsample scheme. And this is a reconstruction from that. It's a very blurred like mass.
But I mean, this baseline is a bit weird because, you know, okay, I say you're doing 128 dimensional space. It's not really RGB. I mean, you could potentially take your 128 dimension image, split it up into, you know, RGB, like treat each 3 dimensions as RGB, you get 42 of them, something like that, right? 42, 43 of them. And then you treat each of those as a JPEG, or do JPEG compression, each of those 43 images. And that will get you a set of, because that will be giving you, you know, a good compression as best as you can with a discrete cosine transform. Right? It's not neural network, it's the best classical compression if you use like JPEG 2000 on those 43 sub-images. And then you can always, I mean, that's a lossy compression, but you can always uncompress and then put it back together again. So that would be to me like a reasonable baseline, because your nearest neighbor, you know, it's like something you just made up. I don't know if that's used in, is that used?
I think it's not a compression scheme, but I use this is basically I want to show like under the fixed like latent spatial budget with like 1616, and there's the fix and it's like same with other like encoders kind of variance that they produce, and it's like its embedding is like better than this very simple
right scheme. No, I understand that. Yeah, I'm just saying for the baseline you need to be careful to choose something that's credible, that, you know, that because there is structure in the latent space, as you can see. If I were to use an RGB image, I could represent that as an RGB image using JPEG compression quite nicely, right? So the suggestion is to look at, that's a very simple thing to carry out, because to make it into a JPEG, a set of JPEG.
But for like JPEGs, it's essentially a quantized version of the precision, right? For JPEG compression. So it's like,
what do you mean the compressed version?
Because here I just want to like mimic this design, like this encoder decoder design here.
No, what I mean is, let's say somebody came to and said your initial problem statement is your embeddings are too large. So you'll say, okay, fine, you know, treat them as images and run JPEGs through them. It'll give you 40 JPEGs, 40 JPEGs, 43 JPEGs for each patch, and then you can uncompress them and use them, right? So that would be like a way to do that.
But like that could be like some like thing to try. But like one thing is for JPEG, I tried, and I think the compression ratio is not it's like
so you have tried it.
Yeah, I've tried it. I think it's only like it can compress like to 60%. So
by 60%.
Yeah, like the compression version versus the original version is 60%.
Okay.
But for this MIM framework, it can compress to 10 to 1.
Okay.
So like 10%.
Okay, so again, if you did try it, you should put the results in.
Yeah, I tried like, but it only shows like the compression, like the difference between like the compression ratios, but it doesn't show like how it can be done for like downstream tasks.
Well, the downstream task is just uncompress and induce it as before.
But one downstream task, I use like the latent representations as the input.
Mhm.
So I don't know like how JPEG compression could like produce like a latent space that I could use.
Oh, you want to use the latent space
Yeah.
after compression directly?
Yeah, yeah.
Okay.
I think there are like two goals. One is for compression. So for compression, it can be used in like reconstruction based tasks where I use reconstruction as the input.
Yeah.
And the other is like enhancement where I can investigate whether
Right. So you can't do
it's
enhancement, you can only do compression with JPEG. Yeah.
Yeah, but for JPEG, it's only concerned with the compression, and it doesn't have the encoder decoder like architecture I'm thinking of. And also, I don't know what would be the latent space like. So I just like artificially construct this NNI compression to see, if I fix the spatial resolutions and use a very, very simple aggregation of spatial information, what benefit can encoder be like, can MI like be better at?
Okay.
So, I don't know. I think it's reasonable in a way that I can just compare it, but it's not very meaningful.
Yeah.
Yeah, I guess.
Yeah.
But I think I will add some figures of compression ratios into my final dissertation to show that this can compress more.
Yeah.
So, and here are these reconstructions, like images from different encoder configurations. So this means the compression, like the ratio, the latent space versus the raw original, and with the patch size and mask size. So as you can see under the same like ratios of compression, I think Swin and VIT kind of does the same at 10%. So they're like resemble the raw embeddings, and it's significantly better than the NNI compression and reconstruction. But they all seem more like blurry and kind of overly smooth. So I guess for MI, I'm like, as far as I'm training it, it's more like it can capture gross kind of interpolated representations instead of focusing on like local sharpness and fine-grained spatial details. And at 2%, I think Swin does a lot better than VIT. And I feel like that's because of it has this hierarchical representation, which allows it to capture different level of details. And so that's why it produce more robust like latent space that preserve more like information that it could be used for reconstruction. And that's the corresponding latent resolutions. And that's how I compute the ratios for the latents. Yeah. And does anyone has any questions so far? Later I will move on to like how I use this on different downstream tasks instead of just comparing it like visually.
You should also introduce what loss function you use to train that. Are you using like MAE or are you using like cosine singularity metric?
I think I use L2, like the L2 loss, which is like MIC, like mean square error, because it gave like a average deviation between original one and reconstructed one, and it will penalize on the large like error. So it gives such like a smooth kind of interpolated version of reconstruction. Yeah. So next, instead of just looking at reconstruction, I want to see how they perform at some of the downstream tasks. And here is like the general like overview of the pipeline. So I first sampled from like globally from sample a lot of raw TESSERA patches and use them for the MIM training to get reconstruction and loss is computed based on them. And they produce like two representations. One is the latent and the other is the reconstructed. And I use both of them for downstream tasks. And I also compare their performance with the raw embeddings to see if there are any improvements or does it match or is there any downgrade. And here are the three downstream tasks I tried. First is the TreeSAT-AI. It's a classification task. And I will first introduce this because this is the only task that use the latent representations. And the other two are segmentations and regression, but they're all like pixel-wise based tasks. So they're like dense prediction. And I have I only can use the reconstructed embeddings because it preserves the spatial dimension. So first I tried the TreeSAT-AI, and the pipeline is more like a probing process. So I free this pretraining encoder and use the latent space with like an MLP head to produce multi-hot vectors which correspond to like a multi-label target. And the matrix I'm using is the weighted F1, and F1 is a harmonic mean of precision and recall in classification tasks. And the weighted is based on their sample proportions of different classes. So you can have the information of all classes together in one matrix. And I think it's mostly resemble like the practical case where like data if you have different samples.
And is this a biased data set, or is it unbiased? How when the data evaluation are some classes more prevalent than others?
Yeah, some classes are more
okay. So in that case, the weighted one would be better than your macro.
The macro or like micro. So
yeah. Okay.
And here are some results in like a Gaussian study grid. So you can first look at the first. Let me introduce the x-axis. So the x is the matrix is the weighted F1, and it's the higher the better. And the x-axis are all these parameter values. And for each line, each like colors represents encoders architecture. And for the group of points that share the same axis, I like kind of offset them a bit to avoid the visual overlays on the graph to show it more clearly. So for the first three figures, it has both the results from Swin Transformer, so you can see Swin and VIT, as you can, and and the dotted blue lines, horizontal blue line, is the TESSERA baseline performance. So from the first three figures, I think VIT consistently outperform both the baseline TESSERA and the Swin encoders. And just to remind you, I'm using the latent representation here. So for this Swin and VIT, they use the latent representation as the input, but for TESSERA, it's used the raw TESSERA. And here I show the compression ratios. So, there's like 1 point because a TreeSAT-AI is a very small data set. So each patch is only 6 times 6. But I trained the encoder, so it only accepts input with spatial size of like multiply of 8. So the spatial resolution have to be a multiply of 8. So I first upsize it to 16 times 16 and then produce the latent space. So under patch latent size of 16 is actually 2 because it's 16 divided by 8. And this is 1. And this is the latent size ratios compared to original. So as you can see at 15% like ratio, the latent representation is better than the TESSERA baseline. So I guess one takeaway is I think VIT representation is like better. So I think it's better at capturing this high-level semantic information that can be used for classification tasks. And the other is I think it shows a bias towards like difficulties of pretraining. So as you can see with like higher compression ratio with higher mask ratio, and it gives better performance. It shows like a positive trend. So it can like the more challenging the MIM setup is, like it actually produce more robust and better representations that can be used for this downstream task. So it's really like interesting because it really shows that this framework is like really trying to learn something out of it. And it has some potential maybe to generalize and this like latent space can be like generalized to other downstream tasks because it's reason to there's gone through like things that they have more things that they have come kind of higher understanding of the task instead of just do the interpolations. And here the patch size and mask size are Swin only parameters. And I think for the patch size, it shows that maybe some pixel level information are like also still important here. and the mask size shows like little kind of impact on the performance.
I just want to check on this. When you show these graphs, are you doing just one run or do you do multiple runs?
I think I did multiple runs.
But you're not showing me the confidence box.
I tried to show it, but it's so small.
It's all small.
It's
Okay,
so
fine.
small.
You should
Yeah,
run
so
that,
it's being covered by the dot.
Got it.
Yeah,
Okay,
it's
very
like
good.
really, really small.
No, that's very good.
But I for each experiment I ran it like 3 times with
Okay.
different seed. But here it's just so small, so I can't
Okay.
really show.
3 runs is not going to give you any confidence bars in teaching effect.
But the 3 runs are already quite small, and I actually, I don't know, maybe I can try with more. But
Okay, that's all right. But just to say that we don't want you to win just because you're lucky.
yeah, but I think it does show something. But if you zoom it really, if you see this, you can see there's like a
Yeah, I
like
see
arrow
that.
bar here.
Yeah, I see that.
Yeah, but it's being covered by this.
Okay. That's fine.
Yeah.
That's all right.
And for the last 2 tasks, they're both like dense prediction tasks, and I use a different downstream model called UNet. It's particularly useful for tasks like semantic segmentation, and it also has this encoder and decoder architecture, with encoder like downsampling the input to like a latent space and upsampling back. But it also has the skip connections to append the input to the output, and so in the later upsampling phase, it can preserve some more like fine-grained information that could be lost during downsampling, and that's why it's very useful for segmentation tasks. And here I introduced it because I not only use it for downstream models, but also I actually try to do it with I'm like pretraining and then fine-tune it for downstream tasks to see if like the mask image modeling could bring some benefits in the ways that allow it to use useful feature. But I will introduce it later. Now you just need to maybe kind of guide the idea of this models. Yeah, this model. So for like the last 2 downstream tasks, actually, there are like 2 kind of evaluations strategies. So one, I call it probing. It's similar to what TreeSAT-AI is doing. So it has this pretraining phase, and then I've used like a kind of like frozen inference stage where I produce the latent representations and the reconstruction, and I use them for like as input to task-specific downstream models. That's like one way of doing the evaluation. And for the TreeSAT-AI, I use the latent space instead of the reconstructions. But for like fine-tuning, actually you can try with first having like a mask UNet to do the pretraining, and then you load the weights to the downstream task. So you have this loaded pretrained weight, and to do a supervised fine-tuning with task-specific head, and see if I see how the performance is to do like evaluate it on downstream task.
I'm sorry, the slide is just very confusing. Why are you doing 2 different approaches? What's the motivation?
I think the motivation is because for this task, if I'm just doing this like probing method, if I'm just using the frozen in this like frozen method, then I'm just using the reconstructions as input to the downstream models. Then I can show the results later. Actually, I think I plan to first like introduce this left part and then come back when I got to the like right part to see like why that's like essential for me to prove that this pretraining has some benefits. Yeah.
Okay.
Because if I'm just doing this part, I feel like the original sensor embedding is a very strong baseline. So it only measures the reconstruction fidelity. So as far as you can get close to reconstruction, you win the task. Yeah.
So you mean enhancement doesn't help you then?
Yeah, there's no enhancement, but enhancement can only be manifest in the fine-tuning phase in this setup.
I see. Okay.
So yeah, so I introduce like past this task. This is like a probing method pipeline. So I first have this pretraining phase, and I use the downstream model as UNet to take the baseline TESSERA input or the reconstruction and get a segmentation map and like optimize end-to-end on this objective for this task. So the target is a 128 times 128 semantic class per pixel tensor. And the matrix I'm using is the mean interaction over union. It's a standard matrix for segmentation. Yeah, so yeah, that's the pipeline for, and I'll come to this later. But this, like the first 5 figures shows the result from the first, like from the probing setup that I described earlier. So as you can see, the blue horizontal line is the TESSERA baseline, and the gray one is the NI compression reconstructions. So here I compare the performance of different reconstructions. So I think the reconstructions from NIM setup it doesn't match the performance of the baseline TESSERA throughout all this experiment. And at this point, for a compression ratio of around 9.5, I think it's preserved 90% of the performance, because this is like 0.5 and it's like 0.45 times 2, like 90% of the segmentation's performance. And it shows a simplicity bias. So the more easier the setup is, the better the performance is. So the easier setup is like lower compression ratio, lower mask ratio, and a smaller patch size, so it can capture the details, and like small mask size gives better segmentation's performance. So it's like really construct with the previous task, where more difficult, more challenging setup is like the kind of the higher, the more robust, the better data spaces. But the reconstruction is only like kind of concerned with how similar it is with the original.
Can you just remind me, VITS and VITT, what's the difference?
Oh, actually VITS is like a larger VIT with more depth than VIT, like VITS stands for small and VIT stands for tiny.
Okay.
But except that they're all like similar, and I didn't put them in the same graph because I only experiment with this VITS in data scaling, because I think we have to use like a larger model for like to process more data to show that it's not a model bottleneck, but rather like a data bottleneck. Yeah. So that's the semantics result. As you can see, it cannot it doesn't match the original embeddings, and it also shows what I'm talking about. It's like only like solely based on reconstruction instead of like the latent representation. I can not tell like how much it learned from the latent space based on this result. So that's why I think it's useful to have like a fine-tuning kind of evaluations. And I think UNet is a very good model for that, because it has this encoder decoders architecture that can be used for MI pretraining. And it's also a good model, downstream model for this downstream task. So there's no mismatch of like architectural mismatch between it. So I also have this pipeline where I first do the MI pretraining on this UNet, and then I append like a tag with it on it, and allow the ways to do the supervised fine-tuning task. And here the result is shown in the last figure here. And then as you can see, I think it outperformed the original TESSERA baseline model. So it shows that MI pretraining actually has some useful weights prior that kind of injected that is trained during this process. So I think this shows that enhancements in this framework works. It's like proof effective. Yeah. Any questions? Because this is like I think the takeaway here. Yeah. And for Borneo canopy height is very similar to past, so I won't repeat again. And here the result. One thing to notice is this matrix measures the difference, so it's the lower the better. So the baseline is below, so it's like lower is better. It's not the higher is better. So it shows very similar trend, as you can tell. Like the more, like it's more similar. It's more it is more resemble the original, then it's better. So the smaller mask ratio, the lower compression ratios, and smaller mask size gives better performance here. And I tried the fine-tuned version is also perform on par with the original one and like slightly better. So I guess I can kind of come to several conclusions here. I think the method of using masked auto modeling framework can be proved like work, like can be kind of work here, like with several reasons why. First, I think it produced very strong compressed latent representations as proven in the TreeSAT-AI task. And it also it's also an effective like compression ratio, gives like kind of reasonable reconstruction from latent compressed version. As we just discussed, I think JPEGs and other compression scheme cannot reach that compression ratios, but this reached it and also gave 90% of the performance back. And also from the pretraining, from the fine-tuning experiment, it shows that it has this transferable pretrained ways that can actually boost up the performance a little bit. And maybe some discussions, because I use UNet for fine-tuning, but I also tried fine-tuning on like Swin and VIT, just like naturally get it from my pretraining phase and append with a decoder, like a head or an upper net, to try to do the past task. But actually it's overfit on the training set. It doesn't give a lot of useful insight where it comes like really train on that. And I think some causes or like reason might be there's like a data bottleneck for my pretraining, because for like a standard ImageNet pretraining scheme, it used like 16 million like images, but here I only use at max 30K. So I think that could be a reason. And the other, there will be like a mismatch in the architecture. For example, like this is not good go-to models for semantic segmentation. So that's why I choose UNet and I pretrain a different like UNet to do the task, just to show that the enhancement have some benefits. And that's everything. Thanks everyone for listening. And shout out to Frank, you're the best supervisor. Thanks for all your help.
Thank you. That's very sweet.
Yeah, I can't do this without you. Yeah,
Thank you. Okay, maybe somebody else should ask some questions.
Yeah, I think I've talked quite a lot. Yeah.
Did you try an even simpler model than UNet? So
I think
regression tree type, not regression, random forest type.
I think I didn't try any like random forest. I only tried neural network, and I tried different variants of UNet, like depth wise, like lightweight. But they all like UNet is the go-to model. It's like really strong, so I fixed UNet for like those tasks. But one thing about UNet is it's like actually quite large. It's a large model. It's like 30 million parameters. And it's kind of the same size with what I use for my encoder. So that's why I actually try to like simplify it so a bit. But UNet is very useful for segmentation task. And actually, like I think past TESSERA is a very challenging task. It's very hard to get a good performance on it. And lots of geospatial model tried, but they actually cannot beat UNet as a like very simple model. So that's why I think UNet is kind of like something that I need to use. Yeah, but I try with different.
The question as for the Swin Transformer, the fact that it has like this locally constrained attention is quite interesting, and I would have thought it might have helped with this task. But maybe the nature of the data is not that hierarchical. So why do you think the vision transformer performs better?
Yeah, that's a good question. I think I don't have a very good answer for it. You mean like this graph, right? I think vision transformer does give a like better presentation. I think that's because of the parameter size. I think the vision transformer, it's like has this higher dimension at first, and it keeps processing at this higher dimension. But for Swin, it actually start with like lower resolutions, and so probably like vision transformer has more like model capacity to do more work.
You think it's more flexible as well, perhaps?
Yeah, I guess so. I think this has like a strong inductive bias and a lot of like restrictions. and it's useful for like reconstruction task rather than like having a strong like latent embeddings. And yeah, and also I think the masking scheme in MAE is more challenging than the masking scheme in SIM-M7 because it's like shuffling and dropping. And also it treats a patch as a mask rather than having this kind of, you can kind of tell the relation between different patches. But in the MAE, it's more like shuffling, so produce more regularization during the training phase.
I've got a question. So if I remember correctly, you mentioned that during the masking, if you make the masking task harder, the feature learning appears to learn more instead of just interpolate. And why do you think that is? Or like if there is a point of which you make the masking task too arduous for the model to learn anything in just classes because it doesn't have enough information.
I think that's a good question, because I think now I only use one task, like TreeSAT-AI as a task to assess the latent resolution. So I'm not sure the insight that the thing I found is like sound or it can be generalized to other tasks. So I think I need more samples. So I need to find more tasks that can use the latent representation to show that this is like a grounded, that's like a reasonable congestion. But from this task only, I think that's because actually, but it's because I think I trained for a fixed approach. So I trained for 800 approach for all the configurations. So I'm not like waiting for them to converge. So that I think maybe more challenging tasks means there's less like shortcut from the reconstruction to the from the original to the reconstruction. So the model actually like spend more efforts trying to figure out what is the high level semantics information and try and use this to interpolate rather than just relying on this spatial shortcut. So that's why it's able to produce more robust, powerful presentations. That's my maybe like hypothesis, but I think it needs to be tested by other different tasks to really show there's a general trend. But I think it's consistent with the findings in other papers, because I think in the original MAE paper, it's actually have a study on different mask ratios with the like output, and it shows that the best is like 65%. And if it goes up, then the performance drop. If it goes up, it drops as well. So that's this like good balance. But from my study, I hired I increased the mask ratio, and it still shows like a positive trend. So I guess there's like a line here where you cross, you kind of.
Yeah, but MA is for 3-dimensional. This is the RGB, whereas you have a lot more dimensions.
Yeah, sure. I have more dimensions.
As you mentioned that you're training for a fixed epoch, right?
Yeah.
I mean, it's kind of interesting because I feel like there would be a relationship between the masking ratio and the training budget on how many epochs you have. Because if you have a higher masking ratio, it might just mean that you need a longer training budget, but you might have better feature learning because that's a harder learning task.
Yeah, I agree. I think so, but maybe the pretraining currently is like kind of easy. It's not that difficult, so it converges early before 800 approach. That's why like having a approach actually makes sure everything is converged. But I haven't really tested on. Maybe if I look at the training curve, you can see like the mask ratio was 0. It's actually like not a mask autoencoder, it's just autoencoder with the compressed data, and it converges early. I think that's something that's manifest during the experiment.
On the previous slide you have shown for TreeSAT-AI, I can see clearly like the textures of the trees, but I'm also using this data set. I think each sample is only 6 by 6 pixels. Is this also from the same data set?
I think I grabbed this from the website. I didn't make the.
I think this is a TreeSAT-AI website.
Yeah, I think this is a high resolution image.
Yeah.
So this is the image that they use to annotate the trees species. This is not the 6 by 6 patch. I think this is at least 24 by 24 patch.
But the actual data sample you use for input is 6 by 6.
Yes, 6 by 6. This is just a illustration. I use 6 by 6, but because of my pretraining encoder only accept a multiple of 8, so I first upsample it to 16 by 16, and then go through this process later.
Would you try like to have the masked autoencoder, like you randomly masking out the spatial patches, but for the spatial patches, would you also like randomly mask out some features of the
Oh yeah, you mean like dimensions in
Yeah,
the
yeah.
channels?
Yeah.
I think if I mask a patch, I mask all the channels. So it's like 0 or 1. But it's
Yeah.
interesting to see if you. I think actually it's done in a lot of like pretrainings in the training phase of geospatial model itself.
Yeah.
So this can be sort of like a post-training.
Mhm.
If we already have the embeddings and we kind of post-train, use a smaller framework, enhance it. But actually, I think masking between different modalities is how they train when they are trying to produce a geospatial model.
So I had an idea for compression, which is different from this, right?
Yeah.
Let's say you have you take a patch of embeddings, I don't know, 16 by 16 to take value, right? Now, many of these are from the same geographical region, and obviously the patch is in the same geographical region. If it's crops, it's all the same crop. If it's forest, it's very similar, and so on. So whenever with the embeddings, you very clearly see, at least in RGB, or the first 3 dimensions, the patches which are all very homogeneous. So let's say what I do is this: I just do k-means clustering, right? I keep k very large initially. I just use some kind of clustering and bottom up. And then what you'll get is that you'll find into the dominant embeddings in the full dimensional space, and you create a dictionary which just says these are the 3 kinds of embeddings out there. It's mostly crop 1 and crop 2, or whatever it is. And then for each pixel, you just say, let's say you have a dictionary of 8 values. You just need 3 bits for each pixel to tell you which embedding is there, right? My suspicion is this will work very well. It's not using any neural network. It's just using domain knowledge to say that things are pretty similar. Now, in those places where you have lots of variations on a per pixel basis, that can happen. Then you need a bigger dictionary. But still, let's say you still need 16 by 16, for example, is 256 embeddings. You probably don't more than like 10 or so dictionary values, right? And then for each value, you only have this, let's say a 16 embedding value, you need 4 bits per pixel plus dictionary of 16 embeddings, which is the full dimension. You still get a huge compression ratio. It probably work very well.
Yeah, I agree.
And it might be worth using that as your kind of classical baseline, I suppose. It's not using JPEG, it's not using anything like that. It's just relying on the fact that JPEG is meant for arbitrary images, whereas this is Earth observation. So we're using the fact that it's Earth observation, that there are immense regularities, that you should be able to do this pretty straightforwardly.
Yeah, I agree. I think it's a good proposal, and it's useful for like small data set where you have already like the labels and all this like embedding. And I think one thing I was planning to do was like want to like try PCA like reduction. Like
but you don't need to do anything that's complicated. This is not even PCA. This is just saying, I'm repeating the embedding over and over again with very small changes, right? For each of the 16 by 16 patch. And so I just create a dictionary per patch. And so it's just kind of the naive way of doing it. It's not totally naive, but it's it's certainly easy to do. And because even your NNI is fairly complicated. And this won't give you any enhancement, but it will give you the compression ratio we're looking for.
What do you mean by 16 times 16?
So let's say I take 160 meter section, right? That's 16 times 16 embeddings. There are 256 embeddings in a patch, right? Now I have 256 embeddings, let's say, and I do k-means clustering, right? And I find out which are the most common clusters. And the centroid of each cluster can be the embedding representing the cluster. Right? And then for each value in the array, I just say this is the centroid of which cluster it belongs to.
Does it work for like dense prediction tasks?
Yeah, of course. It's going to give you per pixel embedding back. It's going to give every single pixel. Yeah. So let's say that this is some kind of a 16 by 16 pixels. And what I have is I have some kind of a crop. I don't know, something like this. These are four feeds. This field A, B, C, D, and this is some kind of thing like that, right? So all the pixels in field A will look the same, pretty much, other than some small variations. So all the pixels B. So if I do a k-means clustering, I'll basically get these clusters, A, B, C, D, E clusters. And then for each of them, the centroid represents the value, the vector that corresponds to that embedding in that cluster. Then for this, what I do is I just have a matrix that says for each value, I'll just say A, B, something like that. And then it goes on something like this, and then you have A, D, etc.
Okay.
So,
Yeah, thanks. From my understanding, I think it's similar to nearest neighbor interpolations, right? Because nearest neighbor is usually finding a neighborhood, like finding like within a neighborhood. Like I replace myself with like one from the neighborhood.
It's not the nearest neighbor. I think it's more like a quad tree. I don't know if I mentioned.
it's like a quad tree, except that you're doing it even more. It's not the quad tree. It's even simpler because it didn't k-means first, so you know what the most dominant types are. And then for those dominant types, you just create a dictionary. It's sort of what lambda zip does. This is how we do zip, zip file, and you do zip in text, where you find the most common words, and then you basically use the minimal representation length for the words. That's it's an information theoretic lower bound is what lambda zip does for text encoding. But here we're doing something really simple. It's just saying with each patch, just find the most common embeddings and then replace the entire embedding with just the index into the corresponding dictionary. And then so you just have a dictionary and you have that array, and then you have dictionary and array, etc. Probably, I mean, if you think of this, the wheat field stretching across most of the US, it's just one value pretty much that you have. And it's a very, very huge comparator. And you can make this for 16 as 16 very even large, bigger than 128 by 128.
What's the difference of this compared to just like putting an image into bytecode and sending that to like 7-zip or something?
Putting what sort of one?
Like, make an image into bytecode and then just text encoding the entire thing.
You could do that, except that that would create a dictionary as well. You could do a text encoding based on that as well. Sure. Yeah.
I think this is on the feature level, right? It's like
The thing is, this is taking advantage of the fact that we know that each word in some sense is 128 bytes long, right? Or because we know that, and so it's a domain specific compression where we know some things about the fact what we're compressing. We know, and it's going to be. We know that the same embeddings are going to be repeated in any homogeneous geographic region.
Yeah.
I also asked, how would it compress like just an arbitrary patch?
It would not. If you had an arbitrary patch, each of these would be the same. Then you'd have to have a dictionary with the entire patch, and then you'd have to add it to make it a little bit larger because you have the full 16 by 16 dictionary. Plus, you have to add this. These are fairly small. It's 4 bits per value, so it's 4 bits times 256. Which is 128 bytes. So adding 128 is going to at most add, if it's in a completely arbitrary thing, it will add 0.7% more larger because you have the full dictionary plus 128 bytes, which is not a heck of a lot. So you're just adding one extra to that. 6 plus 257, it's less than 1%. It's probably 0.4%. But in the good case, it will give you a lot of compression where you have repetition. Right, so you will lose slightly, but you will win big. So that's always a good bet to take.
I think I tried zip zip compressions,
Right.
Or like non-zip different variants on like a patch, and it gave more compression than having just compressing a single embedding.
Yes, this
So
is the patch of 16 to 16 embedding.
Yeah, I think I tried. I think it gives only up to like 60%.
Okay, but that's because you're doing zip, whereas again, zip doesn't know what's coming, right? Here I know what the structure
But the
is.
thing is, like, this is not a universal compressor. Like,
Why not?
because you have to get the labels, right? You need to know like which.
You
Because
have the
here,
label,
I
why
assume
do
you
you-
have the label. For like, I mean, arbitrary patch is like a random patch without
Yeah.
any label. It's like unlabeled patch.
I don't have any labels here. I'm just telling you, for instance, if you give me a patch,
Oh, you mean like cluster it and then.
yeah, let's say cluster it again, and all I need to do is to find out the centroids of the clusters.
Replace it with.
Yeah, replace it with the index of the centroid of the cluster, and then you have a dictionary of centroid values.
Okay.
So sorry, Fisher, but I have one question.
Yeah.
Can I just go on the line?
Yeah, of course.
I understand your method. I have one question. So let's say we have the patch here. Let's say this part is a river.
Yeah.
This part is also a river. There are essentially two clusters, right?
Yeah.
In the embedding space, if you're using k-means, they must be the same cluster.
Yeah.
You see, because they're all.
Yeah, understood. Yeah.
So let's say if they're the same cluster, then ideally what you do is that you will use the centroid of these two clusters, let's say, which is here to represent it. But then how do you reconstruct it? Because I mean, if it's only like a single,
Oh, no. Okay. I'm doing centroid in the embedding space, not centroid in geographic space. So okay, let me be more clear. Okay. And then just the other I think you're right in what you say is correct, but I'm going to tell you again. You can probably stop the recording. Nobody can understand anything anyway. There should be a stop recording button somewhere.
Bye.
Okay.
Oh, I stopped it.
Wait.
it's still recording.
Still.
Bye.